Hello again, Physics 30s. In today's lesson, I'm going to talk about what happens to a wire that carries current through it when you put this wire in a magnetic field, and then we'll use our understanding of a current carrying wire to explain how a device called a current balance works. Learning outcomes, as identified by the Physics 30 program of studies, are 1. Describe and explain qualitatively the interaction between a magnetic field and a moving charge, and between a magnetic field and a current carrying conductor. I bolded current carrying conductor because that's the focus today. We talked more about just a single moving charge in the previous two lessons. And 2, explain quantitatively the effect of an external magnetic field on a current carrying conductor, which means we're going to derive a mathematical equation we can use to calculate the deflecting force on a wire. Let's start off with this familiar scenario where you have a couple of jumbo permanent magnets, and I have a north pole on the left-hand side and a south pole on the right-hand side. And as we know, magnetic field lines emerge from a north pole and go into a south pole. And what I have in this picture is this little circle. Instead of representing just a single electrical charge, it represents a current carrying wire with a bunch of charges passing through it. If I want to draw what this looked like, I can make up a little tiny Cartesian grid here. We could say this is like Y, this is X, this is Z, just to show it at an angle. So the current carrying wire would be aligned in the Z direction. Something like that, but we don't need to actually show it in this manner. I just want to illustrate like what direction the current carrying wire is in. And we do that just by showing the wire cross section, and we have current that is going to pass through the wire. Now, in dealing with current, it means conventional current. And I'm going to talk about a hand rule just in a moment right here. And immediately once you see the word current, you should be thinking of using your right hand for one of the hand rules. So we can use the third hand rule again to predict what direction a magnetic deflecting force is going to be on this wire. Again, there is a magnetic deflecting force because there's two magnetic fields that are interacting. The magnetic field due to the jumbo bar magnets, and we also have the magnetic field due to the moving charges through the wire, where each one of those moving charges in the current produces its own magnetic field. The hand rule pretty much works identical to how we used the third hand rule before. In fact, that's why I'm still calling it a third hand rule and not a variation of that. And the way we'd apply it is, 1, take your thumb and point it in the direction of your current or electron flow. So let's summarize this as we're going through here. So once again, we're going to use its current, I, which means use the right hand. And we start off by taking our thumb and pointing in the direction of current. So the direction of current, which is also I, would be the X means into the page. Two, take your fingers, and your fingers still represent the direction of the magnetic field, the external one. And if you look at the picture right here, the magnetic field lines are going from left to right. That would be towards the east, if we use our 3D vector notation, or the right side of the page. The direction of the magnetic deflecting force is just going to be the direction that your open palm faces. So FM, open palm. And let's try to do this now. So take your right hand, and again, when you use the third hand rule, you need to make sure your thumb and your fingers are as perpendicular to each other as possible. I'd start off by taking your thumb and pointing it into the page. And then you're probably gonna have to like twist your hand or your wrist around so you can get it so that your thumb's pointing into the page and your fingers are pointing towards the right side of the page. If you do this correctly with your right hand, because we're dealing with conventional current, your palm should be facing towards the bottom of the page. The bottom of the page, the 3D vector notation, we're going to call south or bottom of page. We're not going to refer to it as down. Down would actually be the direction of current. That'd be vertically downward. Vertically downward would be into the page. So deflecting force acting on this entire wire is going to be straight down. Now, just a note about the actual wire. If you looked at the current carrying wire, and let's just look at electron flow because that's what's actually happening. It's electrons that are moving, not conventional current, which would be the movement of protons. If you have like an electrical current, it's a bunch of electrons side by side that are moving in a particular direction for direct current anyways. So I've modeled the wire right here as having, I believe, 7 electrons. Now, each one of those electrons would produce its own magnetic field. Each of those magnetic fields would interact with the external one from the bar magnets, and each one of these electrons would be subjected to a magnetic deflecting force, which is going to be straight, I don't want to say straight down, straight towards the bottom of the page or south. Now, this is like an oversimplification because if you look at electrical current, it's not just like 7 electrons moving through the wire. It's probably like billions or trillions of them moving through. So it'd be like really impractical, obviously, to draw the magnetic deflecting force for every single one of them. So all we do is we just identify, well, what's the combined net magnetic force acting on the whole wire? And we just represent that with one vector. And typically we just draw that vector through the center of the wire in the magnetic field. So we can use as you can see, we can use the third hand rule again to predict what direction a wire would get deflected. And that's the direction of this magnetic deflecting force on a current carrying wire. In terms of the magnitude, we're going to get a new equation we can use to calculate the deflecting force for a current carrying wire. And we can get that equation by starting with the previous equation for the deflecting force on a single charge. I did want to point out one thing, though. I forgot to mention this in the previous lesson. I believe on the physics 30 formula sheet, they write this equation a bit differently. They write down Fm is equal to, I think they have like Q, and they just write down V perpendicular. QV perpendicular B. The reason they write V perpendicular is because you want to take the component of your object's velocity that is perpendicular to the magnetic field. That's what, in my equation, this V sine theta represents. The V sine theta is V perpendicular. So the equation I have just expands it a bit more. And our equation, we can deal with angles that are not just 90 degrees. So we're going to start off with this equation. Fm is QVB sine theta. Let's take the wire, the portion of the wire that's actually in that magnetic field from that previous diagram, and we'll say that we're going to look at one electron as it passes from one side of the wire to another. As it passes through one side of the wire to another, the electron its position would change. So there would be a displacement towards the right from the perspective I've drawn it right here. Now, what I want to do is I want to replace this V in this equation right here with an equation that can be used to calculate the velocity of this electron. We'll assume that the electron is moving at a constant velocity, which for the most part current is, for direct current anyways, it's constant. So our uniform motion equation would just be V is equal to D divided by T. Instead of using D, we're going to change that variable to L. And what L is going to represent is L is the length of the wire, and specifically it's the length of the wire that's perpendicular to the magnetic field. Just like with the equation up at the top here, where we only looked at the component of velocity perpendicular to the field, we're only looking at the component of our length that's perpendicular to the field, because only those perpendicular components are going to be subjected to a magnetic deflecting force. So that's what L is going to represent. We're going to take this equation and we're going to just plug it in for V. So sub 2 into 1. When we do that, we would get Fm is equal to QLB sine theta divided by T, where T is the amount of time it would take the electron to go across that length. I highlighted absolute value of Q and T because we can take those two variables and combine them into another one, which is current. Current is defined as the rate at which charge passes through a conductor in 1 second. When you plug that in, you then get the equation for the magnetic deflecting force on a current carrying wire, which is Fm is ILB sine theta. And once again, just to draw the comparison to how it's presented on the formula sheet, I believe they write it as Fm is equal to I L perpendicular times B. And the L perpendicular, again, would just be forcing us to take the perpendicular component of the wire's length. We're going to apply our understanding of a current carrying wire to two different devices, and we'll break it up into a couple of different lessons. So today we'll talk about a device called the current balance, and in the next lesson we'll, in a bit more detail, describe how an electric motor works, a simple direct current electric motor. The imagery here is of a current balance, and presumably as soon as you're looking at this thing, you're getting extremely confused, and that's totally fine. So I'll just try to break down like what we're actually looking at piece by piece. So the first thing I want to focus on in this diagram right here is there's this board. Think of this board as like a platform of a teeter-totter. And directly in the middle of the board, we could have like, it doesn't show it in the diagram right here, but there really should be some kind of a fulcrum point that the teeter-totter can rotate about directly in the middle. Now, on one end, the left end of the teeter-totter, I have this hanging mass that's like pointing straight down. And the reason it's called a current balance is because on the other end of this teeter-totter, I need some kind of force that needs to act on this end that is going to balance the force of gravity from this hanging mass. Now, it shouldn't come as a surprise to you that the force that's going to act on this is going to be a magnetic deflecting force. And let's talk in a little bit more detail about like how I can actually get a magnetic deflecting force. Magnetic deflecting force is actually going to point in a downward direction here. But let's go through all the steps to explain how this actually does play out. Okay, so first of all, let's worry about this solenoid. So this little picture right here, that is a symbol for a battery. So a battery, you have like a short little line and you have like a long line. It shows a couple of them right here, whatever. If you do a couple of them, it's still a battery. The short end means that you have the negative terminal, and the long end means the positive terminal. The arrow that goes through here means that the battery is a variable voltage source, which means that you can change the voltage. So the batteries you stick into your calculator have like a constant voltage to them, where you can't really change them. I mean, obviously the batteries eventually die off, but when you buy them and they're fully charged, they have a constant voltage. So this guy right here, there's something we could do to like change what the actual voltage is being supplied to this wire. All right, so this is the negative end, this is the positive end, and let's just look at conventional current. So conventional current would be, my current is going to move away from the positive terminal, and it's going to go towards a negative terminal. So conventional current would move along this, and then it would go through the solenoid. And then this A right here is an ammeter. An ammeter is just a device that can be used to measure current directly. And then the current would just go back to the negative terminal. Now, I want to identify why the magnetic field inside the solenoid points in this direction. But since we're dealing with three dimensions, it might be more helpful to establish like a three-dimensional grid. So we'll say this is the y-axis. We'll say this direction is the x-axis. And we'll say, it's going to make this a bit more, I'm going to slant it a bit more so it matches the picture a bit better. Let's make it a bit more like this, and we'll call this the z-axis. To figure out the direction of the magnetic field inside the solenoid, you would need to use the second-hand rule. So my second-hand rule first things first, we're talking about conventional current going through this solenoid. So conventional current means use your right hand. For the second-hand rule, you want to take your fingers and you want to curl them in the direction of current. Now, when you look at this right here, the trick you want to use, because you have to figure out, do you curl your fingers like behind a pencil, or you curl your fingers over top of a pencil? Well, look what the current's initially doing. When I look at the current right here, it looks like it's initially wrapping from behind. Wrapping from behind. And you want your fingers to represent that curl. So your current is going to be represented by the curl of your fingers. So the way I would do this is I'd take a pen or a pencil, take your right hand, and then what you do is you would wrap your fingers from behind your pencil. And if you do this correctly, your thumb should point towards the right. Excuse me, which would be towards the positive X direction. So the magnetic field from the solenoid would point in the positive X direction. And we can see this right here. The magnetic field in here is pointing towards the right. Now, let's look at this board. On this board, there's this little section that's colored blue. So I'm going to highlight this here. This is some kind of separate wire. It's not a wire that's connected to the solenoid. It's a wire that's connected to some kind of battery that has a current of I that's going through it. And this wire lines the outer perimeter of the board. We're going to focus just on three sections of this. So we're going to focus on, just going to go here and grab a different color. We're going to focus on the section that goes from W to X. We'll call that section 1. We'll go from X to Y, which we'll call section 2. And we'll go from Y to Z, which we'll call section 3. Now, what I want to know is all three of these sections of wire are inside of the solenoid. They're interacting with the magnetic field. But only one of these sections is actually going to be subjected to a magnetic deflecting force. And it's all about, so if we look at our equation, so our equation is Fm is equal to I L, B, sine theta. The only part of the wire that's going to be subjected to a deflecting force are parts of the wire that are going to be perpendicular to the magnetic field. So the magnetic field points in the positive x direction. So B is in this direction here. So the only parts of the wire that can be perpendicular to the magnetic field will be a wire segment along the y-axis or a wire segment along the x-axis. If you look at the picture right here, segment 1 and segment 3's, though they're both along the x-axis, they're parallel to the magnetic field. So sections 1 and 3, despite having a current moving through a magnetic field, don't get subjected to a deflecting force because sine of theta would be 0. The angle would be 0 degrees. The only part of this that's actually going to be subjected to a deflecting force is going to be section XY, the part that's perpendicular to the magnetic field. And now we can use the third hand rule to figure out what direction that's going to be. All right, so I'll just write it up here. So third hand rule. For the third hand rule, the first thing you want to do is you want to take your fingers and point them in the direction of the magnetic field. So B, which is the fingers. Your fingers would point in a direction that's along the positive x-axis. So I'll say positive x. Then you take your thumb, and your thumb represents the direction of current. The direction of current, the direction of current that in the wire that's actually being affected is along XY only. So I'll write down only along XY. If you look at this right here, that would be in the Z direction. Specifically, the current, if I look at how the current is being traced through here, it's starting, let's see, what direction is it moving? I think it's starting here, then going up across. So I believe in section 2, it's pointing in the negative Z direction. And then the direction of the deflecting force, which is the direction your open palm faces, so let's try to do this. So what I would do is take your right hand, because it's a conventional current, take your fingers and point them in the direction of the magnetic field. So I'd say the x-axis is just pointing towards the right side of the page. The z-axis, the negative z-axis, would be pointing into the page. So with my fingers and thumb perpendicular, I point my fingers towards the right side of the page. My thumb would be pointing in the negative z direction, which is into the page. And if you do this correctly, your palm should be facing towards the bottom of the page. Towards the bottom of the page would be the negative y direction. So that's going to result in there being a magnetic deflecting force only on that far edge of the board. Let's summarize all these points here. You apply current through this wire conductor, so that's the blue wire, until that downward force of gravity is being balanced by a deflecting magnetic force on the current carrying wire. Again, just envision like you have a fulcrum. It's like a teeter-totter directly in the middle. On this end, we're going to have the force of gravity down. On this end right here, we're going to have a magnetic deflecting force that's down. As long as those two forces are equal in magnitude, that board is not going to rotate. The only part of the wire that experiences a deflecting magnetic force is the portion that's perpendicular to the field. So even though sections of the wire WX, XY, YZ pass through the magnetic field, the only segment of wire perpendicular to it is segment XY. The point of this device is this is a clever way that you can determine what the magnetic field intensity inside of the solenoid is. For the time being, we kind of take the magnetic field for granted. Like when we're solving problems, it'll just flat out tell us it's like 3.0 Teslas. But we don't really question, well, how do you know that like the magnetic field intensity inside of the solenoid is 3.0 Teslas? This is a way we can actually figure out what magnetic field intensity is. And on the next slide, we'll go through a little derivation that shows how we can get this. The starting point for this derivation is going to be of a free body diagram of this teeter-totter or this board. I said here a partial free body diagram because I'm not showing all the forces. On the left-hand side, you have the force of gravity due to that hanging weight. On the right-hand side, you have a magnetic deflecting force in accordance with the third-hand rule. There would be two other forces on this. You would have a normal force from this little like fulcrum that does point straight up, which would be Fn. And this board itself has its own mass and weight. So you'd also have, and we typically draw the, not typically, we always draw the force of gravity for an object through its center of mass. The center of mass in this board would just be straight downward. So then we'd have Fg for the board. If this was a teeter-totter, and I said to you, okay, I want two people to sit on this teeter-totter at each end, and I don't want the board to rotate, you would need to have two people sit on each end, and they would need to have the exact same weight. If they didn't have the same weight, then the board would rotate. So for example, if like Fg was bigger than Fm, I would expect the board to rotate towards the Fg side. The board would rotate in a direction that would be counterclockwise. If these two forces are equal in magnitude, then the board is not going to rotate, and that's what we want. We want there to be no rotation, and that's why it's called a current balance. We want to balance those two forces, the Fg force and the Fm force. To properly show like why this is true, you do need to have an understanding of torque equilibrium and specifically how torque works. Torque is basically a force that causes an object to rotate or twist, but this is not something that's required in the Physics 30 program of study. I do teach it in Physics 20 advanced placement. And if you're wondering how I can prove that Fm is equal to Fg in this scenario, I'll do it at the very end of the lesson after I identify what assignment needs to be completed. So if you're curious to know how the torque equilibrium works. But otherwise, I think it's safe and intuitive to assume that, or intuitive to know that this board will not rotate as long as Fg and Fm are the same. So we're going to start with that. Fm is equal to Fg. Fm is equal to ILB sine theta. That's the equation we derived for the magnetic force on a current carrying wire. Fg is just m times g. We can get rid of this sine theta term because theta represents the angle between the length of the wire and the magnetic field. And the only portion we're interested in it was that length xy, I believe, and that formed a 90-degree angle in comparison to the magnetic field direction. So since theta is 90, sine of 90 is 1, we can get rid of that term. We'll be a bit more specific right here. Instead of calling it L, we'll say it's LXY because only section XY is affected by the magnetic field. Therefore, we have ILXY times the magnetic field intensity is m times g. To calculate the magnetic field intensity produced by the solenoid, just divide both sides of the equation by ILXY. And we end up getting the magnetic field intensity, which is the point of the current balance. We can use it to figure out the magnetic field intensity for a solenoid. One note here, in that equation, because we have two currents, there's the current through the solenoid and there's a current through that blue wire. I in this equation represents the current through the wire that is being subjected to a deflecting force, not the current through the solenoid. That's a different current. So this is the conclusion of the lesson now. You need to complete the assignment called current carrying wires. And if you'd like, you can stick around now and I can explain to you how we can prove that Fm is Fg by talking about torque. All right, so for those who've done AP material before, or those who have not done AP material before, I can quickly explain how torque works. Let's say we have a fulcrum, and I have a little tiny board that's attached to the fulcrum. And let's say that I apply a force just at the end of the board right here, and that force points straight down. If that is the only force that is acting on this board right here, so just think about this. If there's a pivot point on this fulcrum, I pull on this end, this would cause the board to rotate in a direction that is counterclockwise. A force that causes an object to rotate is what we refer to as torque. And we use the Greek letter tau to represent the physical quantity of torque. So this force right here would generate torque about the fulcrum point in a counterclockwise direction. Now I'm going to identify one other thing on this picture. So I'll pick a different ink color. I'm going to draw a vector from the fulcrum to the location of where that force is located. And I'm going to call that vector R. This vector is something that we call a lever arm. In terms of the variables you see here, the way that we calculate torque, this is the definition of torque. Torque is something called a vector cross product, and it's a vector cross product between the lever arm and the force that causes the torque. Now, you probably don't know a whole lot about what a vector cross product is right now, so we're going to expand this a little bit right here, because I want to calculate just the magnitude of the torque. If you take the magnitude of a vector cross product, that is just equal to the magnitude of one variable multiplied by the magnitude of another variable, the second one, multiplied by sine theta. Theta represents the angle between the R vector and the F vector. So in this case right here, they make a 90-degree angle. R points towards the left, F points down, so theta would be 90. Therefore, we can simplify this torque equation a little bit, where we can say the torque generated by this force would just be equal to the lever arm magnitude R times F if theta is equal to 90 degrees. So we'll box that right now because that's going to be our important equation for dealing with this problem. Let's go back to that free body diagram of the current balance. So I'll draw the board. I have the fulcrum here. We'll call the fulcrum point O. I have the force of gravity from that hanging mass, and I have the magnetic deflecting force straight down. If I wanted to, I could show those other two forces acting on the fulcrum. The symbol we use to represent the center of gravity of a rigid body is we draw a circle, put a little cross in here, and shade a couple of these regions in, and we can label this as CG, the center of gravity. And we'd have two forces acting at the center of gravity. We'd have the center of gravity of the board, So we call that FG board. And we'd also have the normal force from that pivot that's pushing up on the board. So we'd have Fn. For this board to not rotate, it needs to be in a state that we call torque equilibrium. What torque equilibrium is if you take the sum of all forces that generate torque about the fulcrum, which is 0.0, then the sum of all those torques needs to be equal to 0. So all those twisting forces would just cancel each other off. That's what sigma TO means. It means the sum of all torque about the fulcrum point. If I look at the picture right here, we don't have to worry about Fn or Fg board, because if you go to the torque equation, you only generate torque if you have a lever arm. So the lever arm is the distance from the fulcrum to where the force is. Well, Fn and Fg board are on the fulcrum, so they don't do anything. They don't generate any torque. Now, Fg and Fm, they are going to generate torque in a specific rotational direction. So let's clarify this. Let's assume that counterclockwise is positive. We're going to expand this torque equation here. Now, for a moment, pretend that Fg is the only force that's actually acting on the teeter-totter. If Fg was the only force acting on the teeter-totter, just think about this. If you pulled down this left end right here, Fg would cause the board to rotate in a direction that is counterclockwise. If Fm was the only force that was acting on the board, and you pulled straight down the right end, it would cause the board to rotate in a direction that would be clockwise. So Fg generates counterclockwise torque, Fm generates clockwise torque. We'll expand the torque equation. So what this means right here is if the force generates counterclockwise torque, we're going to write down a positive sign in front of it. If it generates clockwise torque, we're going to put a negative sign in front of it. So this would become positive, the torque generated by the force Fg, that's from the hanging mass, subtract the torque generated by the magnetic deflecting force, and that's equal to 0. We want these two torques to cancel off, because if they cancel off, there will be no net twisting force, and then the teeter-totter is not going to rotate. We can expand this equation up here because torque is just R times F. So let's call the distance from, we'll say from the center of gravity to Fg is R1. And from the center of gravity to Fm is R2. So this equation would then expand as, and by the way, this is positive because that force generates counterclockwise torque. This one generates clockwise torque. So torque is just R times F. So this would be, the torque generated by the force of gravity would be its lever arm, which is R1, take the magnitude, multiply by Fg. We don't have to worry about the sine theta part, because the lever arm and the force of gravity make a 90-degree angle. The torque generated by the magnetic deflecting force would be the lever arm magnitude, R2, multiplied by the magnetic deflecting force magnitude, which would just be Fm. So R times F, as long as theta is 90 degrees. And it is again. The lever arm and the magnetic deflecting force are perpendicular. That's equal to 0. If I move R2 m over to the other side, I would then get R1 Fg is equal to R2 Fm. And as long as R1 and R2 are the same, which they are in the case of the current balance, the fulcrum is located at the direct center. These two cancel off, and then you would get Fg is equal to Fm. And that was our starting point on the previous slide, where we identified that as long as you're in torque equilibrium, where the twisting forces are balanced, then the intuitive thing would be to say that Fg is Fm. If those two forces are balanced on each side, then the teeter-totter is not going to rotate. So that's a interesting way that we can apply some advanced placement physics to talk a little bit about the torque that's generated about a rigid body. Hope you found this helpful, and I'll talk to you next time.